Hi, everybody. I wanted to walk you through some examples of some of the calculations you're going to be doing in Unit 2, Part 2, where we're going to be talking about the luminosities of stars, comparing the distances of two stars, and trying to figure out which one would appear brighter, the apparent brightness, in the sky. I have examples of these in the unit slides, and I'm actually going to work through those examples so you can see how I approach solving these questions that I've designed. And really, this is a great way for you to start getting practice on how to actually apply the fact that apparent brightness is an inverse square law. And it really does connect the concepts of absolute brightness, apparent brightness, and distance, because the apparent brightness depends on not only how truly bright the object is, but how far away it is. All right, for this, I'm going to be working with my iPad. So hopefully I can share that without any problems. Let's see how this goes. Excuse any issues I have while I try to share that device. And of course, it says that I have to install a plugin, even though I had installed it earlier today, and I've done this several times. All right. So you should be able to see my iPad now. So these are the same examples I have in the unit slides, and I want to go through those. So instead of you just reading the way that I go through them, you can actually watch me work through these. And I can give you some advice on how I approach these questions. Okay, so our first example, I'm just going to read the question. And then what I always do after I read a question is I'm going to break it down and highlight and write down the most important parts. Okay, so far star, very on the nose name because this is the one that's farther away, is 3 times farther away from the Earth than near star is. Far star's luminosity is 9 times greater than near star's luminosity. Does far star appear brighter, fainter, or is it the same brightness as near star when viewed from Earth? So again, I'm giving you information about the distance, the luminosity, and you have to tell me which one appears brighter in the sky. All right. So unfortunately, I don't think I can put all the text on here. So I'm just going to slide this down and I'm going to copy down the relevant information. So I have far star is 3 times farther. So, oops, don't know what's going on there. Far star is 3 times farther away. All right, so I have the ratio of the distances, 3 times farther away, and far star's luminosity. So I'm actually going to write the luminosity of the far star, L far, is 9 times the luminosity of the near star. That's just using an equation to write out this entire sentence here that far star's luminosity is 9 times greater than near star's luminosity. Far star's luminosity is 9 times greater than near stars. So now that I have the information written down, the way that I always break this down is I try to do this in two different steps. I calculate what I call the luminosity factor, and then I have what I call the dimming factor. So let me talk a little bit about what each one of these is before I start using them. So the luminosity factor, the way that I think about this is I'm thinking like, okay, so the farther away star is and obviously going to be the brighter one whenever I design these problems, because it'd be sort of a moot question if I made the star that's farther away naturally dimmer, because then of course it's going to look dimmer in the sky. It's going to be fainter in the sky. So the luminosity factor is just a matter of how much naturally brighter is the one that's farther away. And I usually say, I call this LF for short, and it's 9 times brighter. So my luminosity factor here would be 9. The fact that the luminosity of the far star is 9 times greater than the near star means that if they were at the same distance, it would be 9 times brighter. So the dimming factor is okay, well, the far star is farther away. And as you move something farther away, it gets dimmer. So the dimming factor is telling me how much the difference in distance is dimming the farther away star. And remember that apparent brightness. So the brightness is inversely proportional to the distance squared. And I know that it's 3 times farther away. So my dimming factor, if it's 3 times farther away, dimmer. How many times dimmer? Well, it's an inverse square law. So 3 squared equals 9. And that would be what I call my dimming factor. All right. So now I'm just going to compare the two. The luminosity is trying to make making the star far 9 times naturally brighter, but it's 3 times farther away. 3 squared is 9. So it's getting dimmed. It has a dimming factor of 9. Those two balance each other out. So in this case, they are the same brightness. Sorry, that is some really bad handwriting. Not very used to writing on these pads. Box in my answer. And there we have it. Okay, so now that we have used the luminosity factor and the dimming factor, let's do it again with another question. So example number 2. Star Procule is 4 times farther away. So this time I'm just going to write it as D. I'll call this one D. Let's just write it out. D Procule equals 4 times the distance to Proxime. Okay, so it's 4 times farther away. And the luminosity of Procule is 20 times that of Proxime. So now I've written down the relevant information. So star Procule is 4 times farther away from the Earth than star Proxime is. Procule's luminosity is 20 times greater, so it's naturally 20 times brighter than Proxime. Does star Procule appear brighter, fainter, or the same brightness as Proxime? All right, so I've written down the relevant information, and now I can use that information to calculate my luminosity factor. So my luminosity factor here is really just how many times naturally brighter is the star? Well, it's 20 times naturally brighter. So I have a luminosity factor of 20. Let's do the dimming factor. Okay, so the dimming factor. Remember that it goes with the distance squared. So how many times farther away is it? It's 4 times farther away, which means that it would be having a dimming factor of 4 squared. So the distance is trying to make it 16 times dimmer. If they were at the same distance, and then I was to move the Procule to be 4 times farther away. Okay, so the natural brightness is trying to make it 20 times brighter. The 4 times further away is trying to make it 16 times dimmer. The 20 times brighter is larger. It wins. It outweighs how much it's getting dimmed by the extra distance. So here we would have that Procule is brighter. And I could actually say how much brighter, because I could just compare the luminosity factor to the dimming factor. And that would be, let's see here, 1.2. So it's 20% brighter. It's 1.2 times the apparent brightness. And no, I can't do math. 1.25. 4 divided by 16 is a quarter. Sorry, I even make mental math mistakes sometimes. Okay, so usually I'm not going to be asking you to calculate this part right here. You just have to determine that Procule is brighter. All right, so now we've worked through 2 examples. Let's go to a difficult example. This one, you have to do a little bit of the legwork yourself. So here I have star Alonso is 5 parsecs away from the Earth and has the same luminosity as the sun. So it has its luminosity is 1 solar luminosity. Star Alonzi is 25 parsecs away from the Earth and has 30 times the luminosity of the sun. So its luminosity is 30 times greater than the sun, is 30 solar luminosities. So tracking the luminosities there. Which star appears brighter, or do they appear to have the same brightness? And I always want to compare the far one to the near one. It's just easier in my brain to do it that way. So let's go ahead and start doing some of the legwork, because notice I'm not telling you how many times farther away. In this case, you actually have to figure that part out on your own. All right, so let's write down the relevant information. So the distance to, so the distance for, oops, I'm using A for Alonso. The distance for Alonso is 5 parsecs. The distance for Alonzi is 25 parsecs. And really, I'm going to start by, and let me go ahead and write down all the information. The luminosity of Alonso equals 1 solar luminosity. The luminosity for Alonzi is 30 times the solar luminosity. Okay, so notice that I had all those words just to break it down to these 4 numbers. The first thing I want to do, though, is I want to figure out how many times farther away Alonzi is compared to Alonso. That's my brighter one, a naturally brighter one of 30 times the luminosity of the sun. So really, I want to just figure out the ratio of their distances. The distance of Alonzi divided by the distance of Alonso. So 25 parsecs divided by 5 parsecs. That's 5. So Alonzi is 5 times farther away. And now we've gotten exactly where we started in the previous examples. I just had to do a little bit of the legwork to figure out that it's 5 times farther away. And now we can proceed just as we were before, where I can do my luminosity factor. So my luminosity factor is going to be just compare their luminosities. So here we have 30 L sun compared to 1 L sun. So 30. And notice that I could have used a different number there. You just have to divide them to figure out luminosity factor is how many times brighter is the bright one, or is the naturally brighter one compared to the naturally dimmer one. And now we have what I call the dimming factor. And remember that it gets that the dimming factor is following how much it's going to be dimmed by being farther away. It's 5 times, or Alonzi is 5 times farther away. So and it goes off with the distance. It drops with the distance squared. It's an inverse square law. So 5 squared equals 25. And now compare the 2 numbers. So the luminosity of Alonzi is trying to make it 30 times naturally brighter. But the fact that it's farther away, 5 times farther away, is going to be dimming it by a factor of 25. The luminosity factor outweighs the dimming factor. So I can conclude that the one that's farther away, Alonzi, is, or let me go ahead and change the wording there to be a little bit more precise, appears brighter. I don't have OCD. There we go. So all in Z appears brighter. And you can even figure out how many times brighter, because then you'd have 30 divided by 25, which would be 1, and then 5/25, which would be 1.2. Because I made a mistake, always double check. And again, this is what I want you to determine. This is just showing you that you actually can figure out how many times brighter. All right, so hopefully you seeing how I go through these using this luminosity factor and this dimming factor are, I think, the easiest formulaic way to go through this. It also is playing around with the concepts that are important. I offer alternative explanations on how you can go through these types of problems in the unit slides. And if you would like more examples, you can request those and I can put them in the discussion for week 10. Or if there's a really high demand, I can go ahead and write out more examples like this and use my iPad again. Thank you for tuning in. Hopefully actually seeing these examples worked out is very, very helpful to you. Do expect a few questions, not on exam 2, but exam 3, and also on quiz 5 related to this. All right. Thank you for tuning in.